Hello everyone, welcome to our presentation on optimizing pumping stations. We are going to talk on how to optimize pumping stations with the help of Mathematica and SystemModeler. My name is Pedro Fonseca and I'm here with my colleague.
Hello everyone. I'm Alexandre Lecorneur, working at Suez, also with Pedro.
Optimizing pumping stations is crucial because, pumps are fundamental for a lot of our everyday life. Life is based on water. Pumps move water around. And, this presentation is how to optimize them, how to design them with Mathematica and SystemModeler. A little bit of warning. So, there are no special features being presented, no flashy new version, bells and whistles. Well, just real-world experience from an industrial client of Wolfram research products.
Okay, so pumping station. There are many pumping stations on wastewater networks, water treatment plants, distribution of potable water, and that's what we will be talking about today. A pump is a mechanical device that receives energy from a motor and that transforms this electrical energy into a mechanical energy to push the fluid through pipes. You have an image in the bottom showing a cut view of a pump and also an installation of submerged pumps, several pumps actually on the image you see pumping stations.
What is a centrifugal pump? Move fluids, move liquids. It's typically composed of a motor to supply, an electrical motor generally, to supply its energy, an impeller that is rotating inside a case. Yes, how it works? Well, the fluid goes in through what is called the eye of the impeller. So it gets into the case and approaches the eye of the impeller. The impeller accelerates the fluid outwards and the casing collects that fluid at the outlet of the pump, slowing it down and converting velocity into pressure. So we are going to talk about pump performance curves and how it integrates into a system design, and so we need to understand a little bit of the internals of the engineering of a pumping station. And so typically a centrifugal pump is characterized by its performance curve, that its relationship between the flow rate and the head that it develops, or let's call it the pressure that it develops. That curve has the visual aspect of what we see here, this curve here. And so you can see on this plot flow rate at the bottom, head on the left side, pressure on the left side. There are many other curves that are of interest, the efficiency curve, the power curve, but one of the most important ones that connects to the to the pump curve, it's the system curve, as we can see it here. The system curve characterizes, the system where the pump is installed. Yes, and so the interception point between the pump performance and the system curve gives the operation point of a pump or a pumping station if we have multiple pumps operating in parallel. Here is a typical interface for training, but we have similar on production cases where we can move the system curve by, let's say, symbolizing an opening and a closing of a valve. Yes, and we can see the operation point between the pump curve and the system curve. We can manipulate the frequency of operation and see how it reacts in terms of OPEX, equilibrium, etc. And these tools work great. I mean, it's marvelous to have this interaction within the working environment. And this is, let's say, on a static point of view. Then there's the time domain point of view, that is in respect to the incoming flow rates or the required flow rates, how it operates a long time. Yes, and this is where we are going to focus a little bit more of attention during this presentation. So, talking about time domain simulation, I mean, we need to think about inflows into the pumping station and then the pump's flow rates and how that gap of volumetric flow rate accumulates or empties inside the pumping station and its volume. Yes, and so I mean, we have used a lot of different ways to simulate it, between the simple Excel tools and then more custom-made tools. I have here a simple interface for training, yes, where we can actually, I mean, it's a CDF, yes, and we can just slide the mouse along this plot to draw what would be a typical, I don't know, 24 hours curve of inlet flow rate into the pumping station, and we have the equalization volume along the day, and so on this particular arrangement that we just traced, we would need like 4,000 meters cubic so that to have a full equalization of the volume. But then, I mean, we can play with a system and say that actually we would have starts and stops of pumps along the day, and so we would need less volume. And again, this is just a training tool, already quite useful to explain how a system behaves. But when we are under production environments, we have many more constraints than, well, this tool allows to play with. We have particularities on the ramps up and ramps downs of the pumps and particularities on the pump curves, etc. And so, of course, that we typically need a tool that is, well, much more flexible than just a simple interface like this one. This is why we have programmed multiple codes to simulate pumping stations for the last 15 years or so. And this is, well, very customized code on Wolfram language, a little bit cumbersome. Well, some cases we apply a little bit of object-oriented programming methodologies so that it is a little bit easier to manage, but I mean, it's still very custom-made, not very graphical interface, etc. And we have been living with this for a long time. But I mean, it's the typical code that we all are accustomed to see with the Wolfram language, yes. But well, on the latest years, we have been pushing forward with SystemModeler, because it's much easier to adopt and actually extremely faster than what we are used to obtain with custom-made code.
Okay, so the beginning of SystemModeler at Suez, all you've seen before has been programmed by Pedro. All these beautiful tools. But me, a few years ago, I knew nothing about programming, and I had a project on which obviously the use of SystemModeler would be very efficient. So I was motivated, but with no programming experience. So I started with SystemModeler with the Mathematica fluid library. And that was not so easy. After a few days, I was a bit lost. And finally, also we had a case where we had to use the streams. So finally, we decided to build our own library. We can move to the next slide. Yes, because that was developing our own fluid library was also a good exercise to learn about the Mathematica language for me. We did develop it very simple, just what we needed to do our simple projects at the beginning. And progressively, we did add a bit of complexity, and we still have a lot of improvements, of course, to be done on this library. You can see a small model just showing several controls, water tanks, valves, etc. And we had the support from Ankit, and that was very precious for us, of course. So, intellectual property, well, the goal we have is that all engineers in the company can really use SystemModeler, because it's a tool which is very natural and easy to use. So there's a clear interest for all the engineers to be able to use it. But somehow we want to have a degree of protection of the things we are developing in the library. So we could find a few things to get a degree of protection, and especially with external DLLs, calling functions that are in DLL with licenses.
On the following slides, we're going to see an example of application or a methodology of work that we use to interact with SystemModeler models from the Wolfram language, yes, and how do we put all this together, including CDFs interacting with the model and the like. Well, we're going to simulate a very simple pumping station, and so the first thing we do is to start to load that model within the Wolfram language workspace. So as you can see on the image, we have, it's a very small image, yes, but we have an inflow, and then we have a tank from which 5 pumps take out water, and they pump it to another tank further downstream. It's a relatively small model. It has around 300 variables. But it runs extremely fast. I mean, the first time we run it, the system has to compile the model, yes, and so the first time is a little bit slower, yes. But afterwards, it takes the already compiled object and runs it much faster. Here we are simulating 12 hours of incoming flow rate and starts and stops of pumps to keep the tank within a certain level threshold. And so how it works is that typically a pumping station has different starts and stops levels, and depending on the level, it starts one extra pump or it stops one pump from the ones that are running. So we have here the output. We have prepared a few plots from the let me move our faces away. We have prepared a few plots from SystemModeler already, and we can actually plot them in a very streamlined way. There we have it. So here on the left side, we have the state of each one of the pumps. The ones that are operating are on one state, the ones that are not operating are on 0 state, and so we see that along the 12 hours we have some starts and stops. And on the right side we have, on the horizontal lines, it's the start threshold levels, and so whenever the level passes one of those lines, it will start an extra pump, or vice versa, it will stop an extra pump. And here on the brown curve, that is overlapped by this blue curve here, we can see the level inside the tank along the 12 hours as well. And we can clearly see that the pump's quantity or capacity is insufficient because, the level goes from more or less 0 up to 25 meters in height. Well, of course, a typical tank would have overflown, yes. And so we could say that this pumping station doesn't have enough capacity. So in order to improve the design, obviously multiple options. Yes, the one that we are going to explore here is to install a pump of extra capacity. Well, install 5 pumps of extra capacity. We could simply put more pumps. Well, we could do a lot of different possibilities. Yes. Here we have a CDF that we use to design pumps. Well, we don't manufacture pumps, yes, but most pumps on the market follow some kind of design tendency, design rules, and so we can mimic what a pump manufacturer would be able to put on the market, yes, or is able to put on the market, yes. And so here we have, for instance, a tool that allows us to design system pump curves and efficiency curves, and to simulate what happens when we put multiple in parallel, etc. And so we're going to choose here on our CDF interface a bigger pump. Actually, I'm going to choose a much bigger pump than we had before, like for instance this one, yes. And this is a CDF that we already had, that we used to kind of pre-select pumps, and well, we can clearly see that the pump is much bigger than the previous one. It supplies flow rates. The one on the right side supplies flow rates that are like 2.5 times bigger and a little bit extra head than the previous one. I'm actually going to choose a head that is a little bit lower than I had chose. Okay, something like this seems to be a good choice for our system, yes. And again, still within the Mathematica interface, the Wolfram language interface, we can resimulate the 12 hours in what was just a couple of seconds, and this is amazing. And view the results. Now I'm going to plot both the previous results from the old choice. This is the old choice. I mean, these plots we had already seen them before. And now, well, it is extracting the information from the simulation, and we'll see in a couple of seconds the new one. Yes. And so with these bigger pumps, we can see that we no longer jump to 25 meters of level around 3 o'clock. I don't know, in the morning, in the afternoon, it doesn't matter. And we can actually see a lot of starts and stops of the pumps. Well, probably now we have too much starts and stops, and so obviously this would be a thing to optimize. But what was very interesting to see is that we can use previous tools, or let's say algorithms that were developed on the Wolfram language, and streamline them in the working methodology to apply directly to the SystemModeler way of working, yes, and obtain results in really a few seconds.
Now we will see a dynamic interaction, and you will see that it's incredibly fast. We can manipulate the pump curve through the same CDF tool as Pedro did show, and we have an update of our level, which is being updated in a very quick way. And that's great. That's we can see the resulting max level in the simulation. We can have an idea of the number of starts and stops. We can visually very quickly see the impacts of what we are doing on the pump curve. That's very impressive and very useful, very, very powerful, definitely. So now we will talk about the efficiency of calculating things either within the Mathematica soft or in the SystemModeler. And that can be of importance. What you see now on the screen is a modification, not anymore of the pump curve, but of the surface of the pumping station. And of course, the bigger is the surface, the lower is the level increase. So the surface has an impact on the maximum level that occurs during the simulation. And as you can see, we can have a live manipulation on this and directly see the results on the level versus the time. The Wolfram language can, of course, extract the maximum level for a surface, an area, and it can do that for several areas, because that can, of course, be interesting to have an idea of the max level versus the surface we built for this pumping station. And that's what is being calculated now. You can see that several simulations are being processed because we have 10 cases. And it takes a bit of time. Well, there's the simulation time, and there's also the time probably for the Wolfram language to analyze and find the maximum on each simulation that has been processed. And we should get soon the results of the maximum level versus the surface of the pumping station. Okay, it's here. It took 74 seconds, but we have a nice curve. Well, very interesting. That can help us to figure out which is the best equilibrium. We can do almost the same thing in another way. We can also, in the model, in SystemModeler, add a variable that will be the maximum level of the simulation. And it's very simple to add this variable. And that's what we will do now. We will more or less run the same simulations. But as you can see, these simulations are being processed, but there's no delay, almost no delay between two simulations, because the Wolfram language does not have to calculate the maximum level, and you see that it's much faster. So we clearly see here the interest of having some variables calculated within the Wolfram SystemModeler, within the model, in fact.
So I hope you enjoyed these few demonstrations of the linking we do on the methodology of work we carry on the using of both the Wolfram language and the SystemModeler. We can say that, well, SystemModel rocks. I mean, it's an amazing tool. Modelic is an amazing tool. Combining with Wolfram language, well, it rocks squared, definitely. I mean, the potential is huge. We just showed a little bit of interaction between them. It's very interesting to see that we can use manipulate and the previous done tools with CDF and completely link both environments together, really pushing bits of codes from different moments of our experience with this technology. And it's also very interesting to see that, well, in most cases, it's almost real time. I mean, of course, with a small delay, but it's incredibly fluid, the way that we can make it work. For that to actually be a reality, there has to be some premeditated thinking on how to set the model in SystemModeler, because, well, there's some processing that is much more interest to be done in SystemModeler than in the Wolfram language. That is a more generic language environment. And for instance, well, the example that Alexandra just showed you, pre-processing in SystemModeler, what was the maximum level that was obtained inside the tank a long time. I mean, it was incredibly faster than post-processing the results and extracting it from, within the Wolfram language. Yes, and so this has to be always kept in mind when doing this kind of analysis.
Thank you. We are ready for any questions.
And while we wait for the questions, well, do stay tuned. We hope next year to present a similar case studies, but more focus on automatic optimization and how to extract optimums, Pareto fronts, and similar.
We have a question. What was your first SystemModeler model created? We actually worked first on a simple case with a tank, a control valve. We had also another case almost in the meantime with salinity issues and reverse osmosis. They were small models, very small, just a few pipes, a few valves, very simple. And that we started with this, with many errors, with many trials, not working at the beginning, but after a few trials, it was okay. And we could really achieve what we wanted to achieve.
Can you deploy SystemModeler work in a way similar to using the Wolfram player with suitable notebooks or CDFs? No, we haven't tried it. Supposedly yes, up to a certain point. It's what I think it's called virtual labs in, well, it has been presented as virtual labs in previous conferences. But we haven't done it because, well, we don't need to do it internally. The way we have done it's how we presented to you. That is, we have a full Mathematica license interface, and then we interact with the model, with SystemModeler, either directly by coding typical Wolfram language code, or adding a manipulate. Well, I've called it CDF on a few slides during the presentation, because it was really extracted from a CDF and placed inside in the Mathematica notebook, but we keep it very interactive. Not, I mean, the user codes itself along the way, not pre-mashed for a given use. We are thinking on trying to do it, but we haven't tried it yet.
Just another point to complete the answer to the first question. Was it helpful to do it in Mathematica first? The first model we did with SystemModeler, so I worked on that, and I had absolutely no experience with Mathematica, and I directly worked on SystemModeler with Mathematica. After I came to Mathematica with Pedro.
I have been answering some of the questions through the text chat. There was someone asking, is it possible to share the notebook? We can share the notebook, but the library is well, it's our internal IP, and so we will not be sharing it. At least you can, well, I mean, the slides, you can profit from the text, the few phrases of code that are there. We can leave a couple of the manipulates that were there, but you will not be able to repeat the full processing of the presentation.
And there's a question for you, Pedro, at the end. Did you use bound graphs?
No. I don't even know what you mean by that. I don't know if you can clarify.
We did use what we can see on graphs that were shown. They were predefined in the models.
For the convenience of the presentation. Yeah,
Yes.
for the convenience of the presentation. I mean, we can extract the data from the model directly and then do the plot in Mathematica, in Wolfram language. But just for the convenience of the presentation, to keep it in one line, we preset the graphics in SystemModeler. It was one of the questions that was placed was what we would like to see. Well, we would like to see the transfer of data between SystemModeler and Mathematica faster, if that would be possible. I mean, sometimes to import a lot of data, it takes some time.
And there's one other point we would like to see also, Pedro. It's to have a dynamic view of the model with the tanks ups and down, etc., with the pressures. And I know that it's on the list of Wolfram, but that would be very didactic and very nice to see that.
Indeed. I think our time is up. I'll keep answering to the text questions. Feel free to enter in contact with us. And thank you for assisting.
Thank you very much.